All right, so now we're going to talk about this idea of isospectral flows. Okay, so let's try to illustrate this with an example. So let's consider the following. Y1 prime is 2y4 squared. Y2 prime is equal to 2y5 squared minus 2y4 squared. Y3 prime is equal to minus 2y5 squared. Y4 prime is y2 minus y1 y4, and then y5 prime is equal to y3 minus y2 multiplied into y5. Okay, so you can try to reorganize these components into a tridiagonal matrix. So let's y be written as the following. So this is y1, y4, y4, y2, y5, y5, and y3. Okay. So I'm going to put the components of this system of differential equations. And I'm going to rewrite this in terms of this tridiagonal matrix. So this is a symmetric tridiagonal matrix. Okay. And if you consider y to be this, then this system of equations is equivalent to the following. You have y prime is equal to some function b of y times y minus y b of y, where b of y looks like the following. 0, y4, 0, minus y4, 0, y5, minus y5, and then zeros here. Okay. All right. So of course it's one thing you observe is that b of y is skew symmetric, and that this is essentially the matrix commutator of b of y and y. Okay. So the observation is the following, that the solution of this matrix differential equation remains symmetric and tridiagonal. And what's perhaps even more interesting is that it turns out that the solution has the property that the eigenvalues of the solution stay the same as well. Okay. Furthermore, the eigenvalues of y as a function of t, right, remain the same. Okay, so this is what we mean in some sense by isospectral flows, that the spectrum of this function y, or this matrix value function y, stay the same. All right, so if it was just this particular system of equations, which had this property, you might not be sort of too concerned about this, but it turns out that there is a sort of a nice generalization. It's where you still have this isospectral property. Okay, so let's look at that. Okay, so I'm going to try to attempt to generalize. It's the special case. It's to what are called isospectral flows, which again, it's as the name implies, corresponds to matrix differential equations whose solutions y of t of the differential equation have the property that the spectrum of that matrix is a constant of the flow. Okay. So let's see how you can try to generalize this. All right. So what you want is some initial data now. So let's say you have initial data y0, and this is a symmetric d by d matrix. Okay. And then you have some function b, which is a Lipschitz map. From symmetric d by d matrices, it's like two skew symmetric d by d matrices. Okay. Okay, then if you have those two properties, then the claim is that the following matrix ODE, right, which is y prime is equal to by times y minus y by, right, for t greater than or equal to 0, and y at time 0 equals to y0, right? So this initial value prom is said to be isospectral. Okay, which basically means that the eigenvalues of the solution y of t, right, coincide with the initial data, so coincide with that of the initial data, which is y0. Okay. And then we're going to try to prove this, and the reason why it's particularly sort of illuminating, it's like to look at the proof, is because then you can, as it turns out, you can use it's like the method of proof to then construct a numerical method for it. Okay. All right. So let's try to prove this. Okay. All right. So you probably know, of course, that one way, of course, to construct something which is which has the same eigenvalues is to do a similarity transformation. It's like of the initial data. So let's look for solutions of that form. Okay. So let's consider the following ansatz. It's like for the solution, right? And so consider y of t is equal to q of t y0 q t inverse, okay, where q of t is a d by d matrix function. So it's a function of time, of course. All right. So, and it's easy to convince yourself that if you had a solution of this form, it's like then it would be isospectral. Okay. All right. So, so let's differentiate this and then substitute it into the differential equation to see it's like what we can then say about q of t. All right. So put another way, it's like can you express, or can you find an equivalent representation, it's like to this differential equation, which now sort of is expressed in terms of q of t. Okay. All right. So the first observation is that the time derivative of q inverse, right, is equal to minus q inverse q prime, which is time derivative of q times q inverse, All right, and you can convince yourself of this by so this comes from implicitly differentiating then you'll be able for the time derivative of Q inverse, and you can check that it's given by this. Okay, so that's just where that's coming from. All right, so if with that in mind, it's like you can substitute that into the differential equation, and then what happens when you do that is that you can rewrite this in terms of a differential equation involving Q. Okay, so this implies that Q prime is equal to B, evaluated, of course, on Q y0 Q inverse times Q. Okay, and then for t greater than or equal to 0, and then Q at the initial time is just the identity matrix. Okay, so anyway, so then, of course, by construction, right, y of t and y0 share the same eigenvalues. Okay. All right. So that's not quite everything. All right. So let's just see what else you can show. Okay. So in particular, it's like what you can show is that this Q of t itself has some structure. Okay. It's not just an arbitrary d by d matrix, which is invertible. Okay. So so let's consider z of t, which is Q of t, Q transpose of t. Okay. And then, so directly differentiating this, and using sort of this Q symmetry, of this matrix function B, right, implies that Z satisfies the following differential equation, okay, which is that Z prime is, of course, Q prime Q transpose. So I'm just doing the product rule right now, right, plus Q transpose derivative, right? Okay. So this is equal to Q prime Q transpose plus Q prime transpose. All right. Okay. But we had an equation for Q prime, right? So Q prime is equal to B of Y times Q. Okay. So let me just substitute it into this. So this is equal to B. Again, B implicitly depends. It's like on Y, right? So B Q transpose plus Q. All right. So here I'm going to use write this as. Okay. So I'm using again what Q prime is, which is BQ, right? BQ transpose, All right, so this is equal to B Q Q transpose plus Q Q transpose B transpose, but B transpose is minus B. Okay, so this is equal to B Q transpose is Z plus ZB, well, sorry, minus ZB. Okay, and the minus sign again comes from the fact that B transpose is minus B, right? And we use the fact that QQ transpose is Z. All right, okay, and then this has initial condition Z at 0 is just the identity, because Q, of course, at 0 is the identity. All right. Okay. So the problem, well, not a problem, but it's like, so what happens is that the only possible solution of this is the identity Z of the only solution of this is that Z of t is identically the identity. Okay, and you can sort of see this. It's like from the fact that because Z at time 0 is the identity, right? This just becomes B minus B at time 0. So the differential equation, I mean the vector field vanishes. It's like at time 0. It's like, and it's easy to convince yourself that Z t identically, the identity satisfies this differential equation. All right, and because the differential equation itself has smoothness properties, then it has to be that you have uniqueness, and so the only possible solution is just uniquely the identity. So what that tells you then is that Z of t, which is Q of t times Q transpose of t, right, which is identically the identity, which means that Q is a orthogonal matrix. So this implies that QT transpose is identically the identity, which means that Q of t is an orthogonal matrix, right? All right, okay. All right. So amongst other things, it's like that then implies that y is symmetric, right? So so y as a function of t is just now qy0 q inverse, but this is just qy0 q transpose, right, which is symmetric. Okay. Okay, so let me make a few more remarks about this. So so the remark is the following. So it can be shown that for suitable choices of this b function, that for some choices of b, right, the solution sort of converges to a fixed point. Let's say y hat as t goes to infinity, and that y hat is a diagonal matrix. consisting of all the eigenvalues of y0, of course. And so why is that interesting, right? So that's interesting because in principle, then that is suggesting that if your goal was to, compute the eigenvalues of some given symmetric matrix Y0, you could imagine some numerical discretization of this isospectral flow map, right? Which would then, under discretization, yield an iterative method for computing inside those eigenvalues. Okay, so that's kind of interesting. But of course, in order for such a approach to make sense, what you need is that you need your numerical discretization to have the property that when discretizing an isospectral flow, the numerical method itself respects this isospectral property. Okay, so you could imagine discretizing this to obtain an iterative method for computing eigenvalues. But you need a discretization that is isospectral, right? Which is to say that it respects, it's like this property that, it preserves the eigenvalues. Okay, and the problem is that none of the methods we studied so far actually have that property. So. Have this property. Okay, so let's see how you go about doing this in a little bit. All right, so let me just stop here for now.